Welcome, everyone, filing in our virtual door now. So, ready for some algebra this morning. We're going to get into logarithms this week. We did exponential functions last week. Logarithms are related to exponentials in the fact that kind of like multiplication and division is related, so is exponential and logarithmic. Addition and subtraction, exponents, logs. So, that's what we're going to get into. See, we had our first assignment last week. Let's see how that's looking. Oh, great. Just about. There's a few people didn't get it turned in last week, but most everyone did, and looks like most everyone did really well with it. So good scores to start out the semester. But basically everyone's getting 80, 90, 100% on it. All right. I got a busy week this week. I got bowling practice after school today, and then bowling matches Wednesday and Thursday. So the next 3 days, as soon as I leave here, I'm headed to the bowling alley. Tomorrow's an away match, so I'm actually headed to West to get on a bus to go to a bowling alley. So tomorrow. So busy week, but just a couple of weeks left here in bowling. We'll be over by second week of February. We're almost there. Conference tournaments 2 weeks from today. 2 weeks from today, I will have a video for you to watch for class because I will not be here because the conference bowling tournament is all day long. So we have to be there early in the morning and we bowl all day and get home 4:30 in the afternoon. It's a whole day bowling event. And I still don't have a full girls team. So the girls are going to not be able to qualify for state as a team because I still don't have enough girls. And BHS didn't have enough guys. They were trying to find more guys for their team. Just a couple of weeks left in the season. It's crazy. All right, we got 15. We're missing 6 people at the point. We still got a couple of people who don't have their cameras on. Get your cameras on, folks. I don't want to count you absent because your camera's off, but if I have to, I will. All right, let's get started. We're 5 minutes in. That's our grace period officially, so we'll get things going. Okay, so looking in Buzz at our grade screen as usual. Looks like we're on 5.02, and we have a quiz this week, a mid-module check over the first 2 lessons. So we'll take a look at that before we leave, but we only have 1 lesson, the logarithmic functions. Next week, we'll be graphing both types of functions. And those lessons go a little quicker, so we can do 2 of those in the same week, graphing exponential, graphing logarithms. But this week, 5.02 plus the quiz. So let's go switch back to the activities. We'll open up this folder, and let's check out the lesson that goes with the logarithms. Logarithmic function. So suppose you were to graph the linear function, f of x equals 2x plus 3. It crosses the y-axis at 3. That's what the plus 3 is. It has a slope of 2. It goes up 2 and over 1, up 2 and over 1. So that is a nice linear function of f of x equals 2x plus 3. And we can find the inverse of that. And we can even do it without having to do the equation. We can just graph it and reflect it over the line y equals x, because the inverse of a function is its graph reflected over y equals x, which ends up being the equation x minus 3 divided by 2. So x minus 3 is in the numerator, 2 in the denominator, and that is the inverse function of the original linear function. So why are we talking about that? Well, let's verify the graph using algebra, where you could actually find the inverse. If we start with f of x equals 2x plus 3, we go through the 4 steps to find the inverse, and it ends up x minus 3 divided by 2, which is what we saw when we graphed it. So this same process could be applied to find the inverse of an exponential function. So you knew this was going to get around to exponentials. An exponential function is a function where the exponent includes a variable and the base of the function is a positive real number equal to 1. So let's look at the function f of x equals 10 to the x power. It approaches y as you go negative. It approaches y equals 0, but it never touches it. It just gets closer and closer and closer and closer. It crosses the y-axis at 1 and immediately shoots up. When x is 1, it's at 10. By the time x is 2, it's at 100. So it goes up very, very fast. And by the time x is 3, it's at 1,000. So this is a very, very steep graph on the right side of the y-axis, and it almost flattens out to the left side. To the naked eye, it looks like it's totally flat, but it is going down very, 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 very slowly. So that's the graph of the exponential function f of x equals 10x. So although the function notation is replaced with y in this image, y equals 10 to the x, we could graph f of x equals 10 to the x, and then using that y equals x line, we could graph the inverse. So it would be getting very, very close to y equals 0 here, just like x equals 0 here, just like it got close to y equals 0 on that side. And then this would be going very fast. By the time it got y equals 1, x would be 10. By the time y equals 2, x would be 100. And this is actually the graph of log of x. That is the inverse of the exponential 10 to the x power. Log of x, 10 to the x. So these are inverses of each other. And we're going to play with that and get into that. So this is the most commonly used log function. Y equals log. You could also write it log 10 of x. Now notice they didn't put a 10 there. They just put log of x. Because if there's no number there for the base of the log, it's assumed to be 10. Just like when we don't put a exponent on a variable, it's assumed to be 1. So we're going to learn how are exponential functions related to logarithmic functions. The base change property can help in what kind of scenarios. And the base change property is very nice, allows us to use our calculator for just every problem. How can logarithms be used to solve exponential equations? Okay, let's go to page 2. All right, let's talk about the conversion. Let's start our notes. So I hope you got some pencil and paper. If you don't, here's your chance to grab some. But we have, let's start with an exponential equation like we saw last week. Like y equals b to the x power. Remember, if the x is in the exponent, it's an exponential equation. You have a variable at the exponent. So that could be written as a logarithm, as log base b, so whatever the base is here would be our base here, of y equals x. This is how you convert an exponential function to a logarithmic function. So let's put some real numbers for that. Let's say, let's just use our base 10 that we're used to. 100 equals 10 squared, right? 10 times 10 is 100. So 100 equals 10 squared. If we wrote that as the equivalent logarithm, it'd be the log of base 10, because the base stays the base. The log of 100 equals 2. So what this says with a logarithm, it says if I take this base to what power, it'll equal 100. So if we're trying to figure what is log base 10 of 100, 10 to what power is going to equal 100? Well, 10 to the second power equals 100. So log 10 of 100 equals 2. So that kind of gives you a visual. This gives you the formula of how you convert those back and forth. So I'll highlight that because that's important in our notes. We'll be using that a lot. And this just shows us a practical application with numbers that we recognize to see how that works. So let's look at that in Buzz as well here. So y equals b to the x is the same as x equals log b to the y. Or I put log b to the y equals x. It doesn't matter which side you put the equals on. So why is this important? From this simple log expression, it's possible to rewrite it in an exponential form, and then we know how to solve equations in exponential form. Could be that the exponential may be simpler to solve a lot of times. Certainly a lot of times. We're dealing with logarithms. We're not very used to that, and it gets pretty confusing pretty fast if we've got a whole bunch of logarithms in one problem and we're like, what in the world? So, for example, log 2 of x equals 7. That may be simpler to think about it. 2 to the 7th power equals what? Equals x. What is x? Log 2 of x equals 7 doesn't fall in their mind. All right, Sherman. 2 to the 7th, we can throw in a calculator pretty quickly and get an answer. So logarithms, like exponential functions, do have bases other than 10, because this one was base 2 that it put right there. So the base of a logarithm is identical to the base of its inverse exponential function. So a log with base e, let's talk about that real quick. There is another base. So if we just do this, log of 100, this is base 10. If we do not put a base, it's assumed to be base 10. So anytime you just see log with an argument there, that's base 10. There is something known as a natural log. If we said, what's the natural log of 100? And we didn't, you never put a base with natural log. This is the same thing as base E. So ln of 100 is the same as writing log base E of 100. These are the same. But when you do base E, you just write it as ln, natural log. Because E is the natural number in math. So we don't ever write log E, we just write ln, natural log. And just to refresh our memories on that, it's like E, wait a minute, Mr. Brock, is that a variable? No, it's not a variable. Remember, E is a number. It equals 2.7182818. So E is a number. So if we're finding the natural log, well, here's the log. Let's do log of 100. Log of 100 is 2 because it's 10 squared, right? Just the log. I didn't put a base, so that's base 10. 10 squared is 100. With E, it's going to be a very different number. What? Take the number 2.718, that whole number. What power do you have to raise that to equal 100? Oh my gosh. Well, it's going to be, let's see, 4.6051701. So if you use this as the exponent for E, that'll give you 100. So the natural log is very different. We only use the natural log in specific cases because we don't often deal with the number E. But you do need to understand that is the same thing. ln it's a logarithm, but it's just using base E instead of 10 or any other number that we want to assign it. Natural logarithm, log with base E. So, okay. And for instance, let's look at this. Evaluate the logarithm expression to log 2 of 128. Let's just put that in our notes so we can keep building some examples here. So log 2 of 128 equals x. Well, solving that, it's like, I'm not sure. Let's rewrite that as an exponential, right? So the base, 2 to what power equals 128? See, the base is the base, 2 is the 2. The x, which is in a logarithm over here, is the exponent. This is the exponent. This is the argument. The y goes as the equals. So now this is a little easier to solve. 2 to what power equals 128? Let's pull our calculator out and figure that out. 2 to what power? Well, let's see. Let's try like 2 to the 6th power. Oh, that's 64. We're almost there. So let's raise it one more power. 2 to the 7th power. 2 to the 7th power equals 128. So if we go back and we're solving this and say, okay, so 2 to the 7th equals 128. So log 2 of 128 equals 7. That's the answer. 7 is the answer we were looking for. We were just trying to figure out what number to raise 2 to equal 128. So that's how we're solving this simple logarithm here. Base 2 is fine. We can use any base we want to. Let's see how they step through it. Okay, they rewrote it. Y equals 2 to the x. So 128 equals 2 to what power? And they figured out 128 is 2 to the 7th power. So 7 equals x. Setting as equal bases. They changed 128. That's how we need to solve exponentials, right? 128 is 2 to the 7th power. So 2 to the 7 equals 2 to the x. X equals 7. So 7 equals log 2, 128. Important note. If you are given log base 3 of 9 equals 2, 3 is called the base. So let's get the vocabulary down. 9 is called the argument. I've used that a few times this morning already. And 2 is the exponent. So that is the exponent. The same equation written as the exponential would be 3 squared equals 9, where 3 is the base, 2 is the exponent, 9 is the argument. So logarithms are base, argument, exponent. Exponents are base, exponent, argument. Just those two switch positions right there. So creating logarithmic functions is very similar to creating exponential functions. We'll kind of build this in our notes as well, like we did last time. Except for this time, the f of x goes up by 1 each time. Which one are they doing? Are they doing base 2? Yes, they are. Okay. 2, 4, 8, 16. This time, these are going up by 1, plus 1, plus 1, plus 1. We did this with exponents, except for the x was going up, plus 1, plus 1, plus 1. This time, the function 1, 2, 3, 4, this is times 2. So we see it kind of the opposite of what we saw with exponentials. And so when you look at how the values increase, it's plus 2, plus 4, plus 8, which means we could use times 2 instead. And so we know this must be log 2 of x. So f of x equals log 2 of x. So log 2 of 2 equals 1. So 1 equals log 2 of 2. So this says 2 raised to what power equals 2? Well, 2 to the first power is 2. 2 equals log 2 of 4. 2 raised to what power equals 4? 2 squared is 4. Oh, equals log 2 of 8. Now it looks like not equals because I started to put my L before I put my equals. 2 raised to the third power equals 8. So we see how those fit in. This is the table representing log base 2 of x. And we can continue on with that. So checking their data when x equals 2, when x equals 4, x equals 8, x equals 16. F of x equals log 2 of x. So log 2 of 4, 2 squared equals 4. All right, we're going to evaluate, and this is the natural logarithm we're going to use in this video. So let's take a look at the first example they're going to give us here, just with solving a natural logarithm. We're going to solve natural log of x equals 3.
To solve the natural log of x equals 3, first Rewrite the natural logarithm in exponential form. Remember, the natural logarithm represents a logarithm with base e. The next step is to solve for the variable. Using your calculator, find the value of e cubed. The final step is to check your work. Substitute 20.09 into the original equation to verify the solution. Using your calculator, find the value of the natural logarithm 20.09. The solution has been verified.
All right, there's lots of calculator use with logarithms because we don't know the logarithm of these numbers a lot of times. We wouldn't know the natural log of 20.09. So we'll be using the calculator a lot to solve many of these things. Okay, so now they want us to solve the log B32 equals 5. So this one's a little different. Instead of having one of these numbers as our variable, we don't know the base. So the first thing we want to do is rewrite this. Log b of y equals x is the same as y equals b to the x. So so 32 equals the base to the fifth power. The base to the fifth power. And we're solving for the exponent, which in this case is the b. Well, the way you would do that is you would take the fifth root. Because the fifth root of b to the fifth is just b. And the fifth root of 32, which we can do in the calculator if you don't know that, because we don't think about fifth roots very often. This has square root right there, but if I shift, I can get a y root of x. So if I say, okay, 32 shift y root, I want the fifth root. And they'll say, oh, it's 2, because 2 to the fifth power is 32. So I'm like, okay. So the fifth root of 32 is so base equals 2. So this is log 2 of 32 equals 5. And we can double check that log base 2 of 32. Let's see, does that actually equal 5? Again, I can shift. And when I shift on this calculator, it lets me do different bases. So if I say 32, and it'll say, okay, what base are you using? So I'm using base 2. And it says, oh, yeah, the answer is 5. So 5 does equal 5. Because log 2 of 32 is 5. Rewrite it in exponential form. Oh, here you go. They want us to step through it. Log B32 equals 5. Rewrite the logarithm equation as an exponential. What is the base? Well, the base is b. It was b there. It's b here. What power will the base be raised to? 5. And what number or variable will the exponential equation equal? It equals 32. Then it says solve for the variable. How will you find the value of the variable? Take the fifth root of both sides. Fifth root of b to the fifth is b. The fifth root of 32 is 2. And then check your work. Log b 32 equals 5. Log 2 32 equals 5. 2 to the fifth equals 32. 32 equals 32. So they checked it by making it an exponent from this step. So, all right, page 3. Okay, this is really helpful because, when I was playing with the calculator, I had to shift to get something besides log 10. And some of our very simple calculators do not have that option. You only have log, just base 10. A lot of times you just got a plain little calculator. Every calculator generally will have a log button, but that is only base 10. And we're like, well, what do I do if I have something that is not base 10 that I'm trying to solve? So let's do the change of base. We can change bases. And you will have assignments in our quiz and stuff to where it tells you to use the change of base formula. So let's say we have log b of y. And we're like, well, in our b in this case, let's say is not base 10. It's like, how can I put this in my calculator? Well, this is the same as log of y. And look, that is base 10. I didn't put a base. Divided by log of b. This is our change of base formula, which means if I have something like totally weird in my problem that I don't know how to solve, like log base 3 of 47. 3 to what power is 47? Well, it's not going to be an even number. 3 to the third power is 27. 3 to the fourth power is 81. So this is a decimal answer somewhere between 3 and 4. So that would be hard to find. But looking at our change of base formula, if we don't have a calculator that could do log 3, or we don't want to try to do the log 3, that's just a mess. We can say, well, this is the same as log 47 divided by log 3. That we can do pretty simply in our calculator. Let's go here. And let's just say 47. I'm just going to hit the plain log button. That's just the plain log button. I didn't do log base 3. And I'm going to divide that by 3 log. So there's what it equals, 3.50. We rounded to 2 decimals. Actually goes 4.55537. It goes much more. But it's about 3.5 because we had to round it. Let's see exactly what we would get if we used the shifted log. Let's see, 47, the log base 3. So I can do log base 3. It's the same thing, 3.504553. Same answer. So this one I did it with base 10, log of 47 divided by log of 3. If I don't have the fancy button to make it base 3. Note, let's make a note here. We could have also done it this way. Log 3 of 47 is the same as the natural log of 47 over the natural log of 3. We can use the natural log. Change a base doesn't mean we have to change it to base 10. We can change it to any base. 47 natural log divided by 3 natural log is 3.504. Again, we're getting the exact same answer. And if you want to get really picky, we could, just to be weird, it's like I don't know why we would, but I just want to show you it works, to say we could have said log base 11 of 47 divided by log base 11 of 3. This will also equal 3.50. Change of base means you can change it to any base. I can change this log 3 to base 11 or base E or base 10. It's just we generally always use it to change it to base 10 because this is in our calculator and it's easy to solve. This is harder to solve than just doing this. But it works. Let's go ahead and just prove it to ourselves that that works. So 47 shift log base 11 divided by 3 shift log base 11 is still 3.50455530. See, it's the same thing as what we did right there. So we can get the same answer any base we want to. But the reason we use the change of base generally is because we want to change it to something very easy for our calculator. log 47, log 3. We divide that, get you the same answer as this does if you punch it directly in a fancy calculator. So this is great. In our assignment, our quiz, and probably even our test at the end of the unit, is going to say use the change of base formula. And it'll give you some equation like this, and it wants you to write it like this, and then punch it in the calculator and give an answer. And it'll say show your work. So this is the work you would show. Log 3 of 47 equals log 47 divided by log 3 equals 3.5, 0. Change of base formula. Very handy though, because it makes any calculator very useful to solve these problems. And we don't want to find log 3 of 47 without a calculator. So there it shows that log by equals log y over log b. Change of base formula allows you to find the value of a logarithm with a base other than 10 using a calculator. You can convert them to log 10. These are both log 10. All right, so then it shows natural log. Well, first, before that, it shows the example. So if we have log 2 of 8, you can take log 8 divided by log 2, and the answer is 3, which 2 to the third power is 8. So that's one that we even know the answer to, because we do know it 2 to what power equals 8. But you can punch it in the calculator and get the right answer. Natural log, you could also do it with the natural log on your calculator. Evaluate ln9 using your calculator, round to the nearest thousandth, enter the solution. All right, little calculator practice here. Clear all that. Natural log of 9. There's 9. Hit the natural log button. It's 2.197. It says to the nearest thousandth. Okay, it rounds down to 7 because that's 0.22. 2.197. Great job. Practicing with our calculator. Now, there is a calculator, and we'll look at it when we get to our assignment. The calculator in Buzz, this calculator, I have to hit what I want first, 100 log. The one in Buzz, you hit log first and then 100, and I'll show you. So you just have to figure out with your calculator, does it want you to hit the log button first? Like if I hit the log button now, it's like, oh, I guess I can't put the log button first because it's saying the log of 0 is not valid because 10 to what power equals 0? There's not a power of 10 that would equal 0. So you'll figure out real quick whether you hit the log button first or whether you hit the number first and then hit log. Because they'll give you an error if you do it wrong. So it was looking at ln of 9. It says, what if we did that using the change of base formula? We said that's ln 9 divided by ln e. Well, the natural log of e, here's e. If I take to the natural log of that, it just equals 1. E to what power equals e? Well, e to the first power equals e. Just like if we did log of 10. 10 to what power equals 10? It's 1. Take a few examples to ensure you're understanding the change of base formula. Okay, log 7 of 15. Let's do another one on our notes here. Log base 7 of 15. 7 to what power equals 15? Oh, well, it's a decimal. So that would just be log of 15 divided by log of 7. 15 goes on top. The base goes on bottom. Let's figure out what that equals. Put it over here. So log of 15, log divided by log of 7. The answer is 0.82. Is that right? Oh, no, because I did log of 5. It's like it can't be less than 1 because 7 to the first power is 7. 15. I missed the 1. Log divided by log of 7. Okay, that looks more right. 1.39. 1.39. They said, according to change of base formula, you can divide the common log by the common log. So log 715 is log 15 divided by log 7. Be sure to round to the nearest hundreds, and it's 1.39, which is exactly what we had. So, okay, let's see what their second example is. You could have done natural log, evaluate the natural log of 4, which again, I don't know why you'd put the natural log of 4 divided by the natural log of e, because that's just dividing by 1, but it's also 1.39, looks like, when you round it. All right, page 4. Uses of logarithms with different bases. It's like, okay, so why are we even doing this? What good is this? So when you turn 16, you decide to put $50 in a savings account so that you're hoping it'll grow where you've got $2,500 to put a down payment on a new car. The account has an interest rate of 3% and it's compounded monthly. We want to know how long it'll take to earn $2,500. So last week we looked at this formula. The amount of money would be the starting principal times 1 plus the rate over the number of times per year in T. Like, okay, we know how to do that. We put in the amount of money we start with, the rate, number of times, and see after so many years what's it's worth. This is a different problem. This says we have $2,500 that we want. We start with $50. We're going to get 3%. And how often did it say we get 3%? Let's take a look at that. 3% per year compounded monthly. But we don't know the time. We want to know how long will it have to sit in a bank account making 3% monthly until it equals this. So let's fill in this information into what we know here. The amount we want is $2,500. We know what we want for our down payment for the car. Our starting principal is $50. 1 plus the rate is 0.03. We have to put it as a decimal. 3% is 0.03 divided by n. N is monthly, so it's 12 times a year. NT, 12T. We don't know T. We want to know how many years it'll take for $50 to turn into $2,500 at 3%. Now we need to solve this. Like, how do we solve that, Mr. Brock? Because, well, let's start simplifying. Let's simplify what's inside here first. 2,500 equals 50 times. Let's get out our calculator. 0.03 divided by 12 is that, plus 1. So inside the parentheses is going to be 1.0025, and it's going to be raised to the 12t power. All right, we're getting closer. Let's divide both sides by 50 because we're trying to get this closer to by itself here. Trying to solve for t. So 2,500 divided by 50. You may be ahead of me on this one. 2,500 divided by 50 is 50. So 50 equals, now we just have 1.0025 to the 12t power. Where do we go from there? Well, it's like, I'm not sure, Mr. Brock. We're a little out of my league here. I haven't seen this before. I'm trying to solve for this as a variable. What if we rewrote this as a logarithm? Can we do that at this point, or would it be premature? Let's see. 50 equals this to 12t. So that means if I rewrite this as a log, let me do this way. Log. The base is 1.0025. We want it to equal 50, and right now it equals 12t because that's the exponent. right? Whatever the exponent is goes on the other side of the equal sign with the log. Whatever the exponent is goes on the other side. So since it's 12t right here, 12t will be over here. Now, oh, look, this is just a number. We can put that in our calculator and get it. And if we divide it by 12, that's going to equal t. So t equals log of 1.002550 divided by 12. Okay, we got a weird little base, but we can use the change of base formula in here. We could say that is the same as log of 50 divided by log of 1.0025, and all of that would still be divided by 12, and that's what t would be. Okay, well, we can solve that with just a basic log button now. 50 log divided by 1.0025 log equals 1566. That's what's on top of our fraction. Let's give it a few decimals before we divide. 7643997. We'll go a bunch. Divided by 12. So let's divide that by 12. So the answer to these two decimals. So there you go. We'll have our money for our down payment in just 130 years. It'll only take 130 years. And then that $50 will turn into $2,500, making 3% a month. Yeah, I think we're going to have to get a job. I don't think that's going to do it. 130 years. What do the variables represent? Well, we know A is the amount of money that we have invested in the account after so many years. P is the principal. R is, all right, Olivia, R is the rate. N is the number of times. When we substitute that in, there's where we get the 2,500 equals 50 times 1 plus 0.03 divided by 12, 12t. So then you start simplifying it. Divide both sides by 50. Oh, they didn't get the 2,000 divided by 50. That's funny. They got it messed up there, what it looks like. But 50 equals 1.025 to the 12t. This is where we had it. We had it to that same point. So the equation becomes 50 equals 1.025 to 12t. But 50 and 1.025, to solve an exponential equation, we have to get these to the same base. Have to get those to the same base. It's like, let's just solve it with a logarithm. All right, let's see. What do they want us to do here? Let's look at another problem. 4 equals 7 to the x plus 1. If we write that as a logarithm, log base, oh, that's a terrible G. Yeah. Like, slow down, Mr. Brock. Make sure your fingers are working this morning. Log 7 of 4 equals x plus 1. 7, the base is the base. 4 becomes the argument. The x plus 1, which was the exponent, goes over here now. All right, so we'll rewrite that way. Let's see how they want to solve that. So that's the first thing they did. Make that a logarithm. Step 2, use change of base to where we can solve this very simply with our calculator. So this is log of 4 divided by log of 7 equals x plus 1. We just simplified that for our calculator. So step 3 is to do the math. So let's put that in our calculator. So the log of 4 divided by the log of 7 is 0.7124. We'll go that many decimals. Equals x plus 1. So then we just subtract 1 from both sides. And x will equal See, minus 1. 0, negative 0.2876. We'll round it to 4 decimals this time. 288. They round to 3 decimals. So our 2.78, it would round to 288 because 6 would make the 7 round up. But we just use the change of base formula. So log of 4 is 0.6020599. Log of 7 is 0.845. When you divide those, it's 0.712. So then they go back to the problem that we just solved a minute ago. If we had this, where we got it down to 50 equals 1.025 to the 12t, we rewrite that as a logarithm, log base 1.0025 to the 50. We can take this log 50 divided by log 1.0025 and then divide that by 12, and it's 130 years. So we got 130. So when identical bases do not exist and cannot be made, right, there's no way we can make 50 and 1.025 the same. So last week we learned if we can make those bases the same, we can solve it as an exponential equation. There's no way we can make 50 and 1.025 the same base. So that's when we can switch and use logarithms to solve that. How about solve e to the 2x equals 30? Oh, that's a good one. Okay. E to the 2x equals 30. Okay, so if we rewrite this, the base is e. So if we said log of e of 30 equals 2, it's like, oh, that's not it. Log of e. Well, log of e means that's just natural log. Oh, equals 2x. I'm sorry, equals 2x. So natural log of 30 equals 2x. Divide both sides by 2. So whatever the natural log of 30 is, divided by 2, is what x is. Because log of e is the natural log. We don't have to put log e, we can just put natural log. So when we rewrote this as a logarithm, and again, the only way this is going to get easier is to practice. The natural log of 30 divided by 2, 1.70. So let's compare to what their answers. And if you need to go back and look and see what they did in the lesson, when you're working through these, please do that. So isolate the variable. Look, natural log of 30 equals 2x, just like we had. So you divide it by 2, 2x equals 3.4, and the answer is 1.70. Round it to nearest hundredth. It's like, okay, this logarithm stuff, Mr. Brock, I know. You just have to step through it slowly, practice. Okay, this goes back to the a equals p1 plus r to the t, where it's just once a year. The n must be 1 because we don't have an n in this equation. So a is the amount after the exponential growth or decay. P is the starting amount. 1 plus r is the rate of change. Is it going up 3%? Is it going down 3%? It's either 0.03 or negative 0.03. Remember, if it's less than 1, when you add it to 1, it's a decay. And t is time, usually years. Changing time increments. Okay, we looked at that a little bit last time. Let's look at this again here. Use this function to represent lizard population. 14 to, okay, so let's write down our equation. We can tell that if this represents our lizard population, we started with 14 lizards. And it looks like they double every time period. If this is years or this is months or whatever the time period is, since it's times two, they're doubling. So if this is doubling every year, and we want to say 5 years, it'd be 2 to the 5th. How many lizards would have if every year they're doubling? So that's our starting equation. It doubles every year. So now we want to know what's the population going to be each month. Each month. So here's how we would do that. It's like, okay, well, if we want to know, this is year, double each year. Okay. What about each month? So we can convert this. Say, okay, well, if it's each month, L of t. So we can say, if we want to break this down to a month, we just say 14 times 2 to the 1/12th. What is 1/12th of doubling? Right? 1/12th power. And then we would say 12t. So 1/12 to the 12th. Remember how that works? Like if we had x to the 1/12th raised to the 12th power, 1/12 to the 12th, the power to a power principle that we had previously last week says we can, if we have a power taken to a power, we can multiply it together. 1/12 times 12 would be 12/12. So that's just one. That's just x to the first power. So that means we did not change the equation. We just rewrote it. Because 1/12 to the 12th is just one. So this is still just 2 to the t. But we have changed what it looks like in order to convert it to each month. So LT equals 14, 2 to the 1/12th raised to the 12t. And then we can convert 2 to the 1/12th to a number here. 2 to the 1/12th. If we remember this, when we said if we had x to the 3/4 power, that's the same thing as the 4th root of x to the 3rd. We looked at that, converting between a radical and an exponent. Whatever's on bottom of the fraction would go outside to be the 4th root. Whatever's on top would be the power that's raised to it. So if we have 2 to the 1/12th, that is the 12th root of 2 to the first power. It's the 12th root of 2, which would equal, well, let's see, because that's going to require a calculator. Shift, and it wants to know which root I want. I want the 12th root of 2. So that would be 1.0595. Let's just round it into decimal. 1.095. So this equation becomes LT equals 14 times 1.0595 to the 12t. And that's how much lizards you have each month. This is now converted to a month by month equation. Instead of every year they double, which means every month they get 5.95% more lizards. How many months do you want to look at? You want to look at 6 months? Take this to the 6th power. Well, 72 times 6, 6 years. 6 months would be 0.5, so this would be a total of 6. If you put 1 year, then it would be this to the 12th power, 12 times 1, which will bring you back to this. But we can do a change of base. I mean, change of time period, changing time increments. By just adding this 1/12th and this 12th, and then simplifying it. What is 2 to the 1/12th? If you know how to use your calculator, you could probably do 2 to the 1/12 as well. So 2 raised to the power of parentheses 1 divided by 12 is still 1.059. Same answer we got is taking the 12th root of 12. 2 to the 1/12th power. So 5.9% is the rate of growth each month for the lizard population. And then here's another one where the sailboat decreases 12% a year. Find the decay each week. So you can go through that example and say, okay, well, I would add a 1 over 52 and put a 52 outside. Then when you simplify that, it would decay 0.002 each week. Each week it would have 0.998% of its value. 99.8%. Let's look at the lesson summary. Then we need to look at some practice problems, our assignment, and the quiz. Okay, to solve a logarithm or evaluate an expression, rewrite it as an exponential. Rewrite the exponential equation as a log. Solve for the variable. Check your work. A log function is the inverse of an exponential function. Y equals log bx, where y is the power, b is the base, x is the argument. Logs of base 10 are written without the base. You just write it log of x. Logarithms of base e is written as ln of x. And here's how you convert back and forth. That's in our lesson summary here. Y equals b to the x is the same as x equals log b to the y. Here's the change of base formula. Log b of y equals log y divided by log b. To solve exponential equations with unequal bases, write them as a logarithm and then solve it. And then to convert the time interval, you do 1 over c and put a c outside, because those will cancel each other out. Let's see what kind of practice problems they give us for this. They give us 2 pages of practice problems. First one says, solve this logarithmic equation. Select the correct choice and see submit if you're correct. Log base b of 1,000 equals 3. Let's do that real quick. Log b of 1,000 equals 3. Well, let's rewrite this. The base is the base. What's over here is our exponent. What base to the third power equals 10? Take the third root. This is b. And what times itself 3 times equals 1,000? It's 10. 10 is the third root of there. 10 times 10 times 10 is 1,000. So we know our answer on that one is simply 10. So there are 4 practice problems there. Log x equals 1. What does x equal? Oh, that's a good one because it didn't give you a base. They didn't give you a base. What's the base? It's 10, right? So this is log base 10 of x equals 1. So 10 to the first power equals what? So there's 4 problems, like I said. Let's look at the next page and see what kind of problems it gives you there. Oh, activity 1, activity 2. Solve each of the following exponential functions. Round to the nearest hundredth, so 2 decimals. 5 to what power equals 20? Oh, how would you do that? Convert it to a log 5 of 20, and then use change of base. Second problem, 6 to the x minus 7 equals 9. Convert it to a logarithm. Solve for x. Activity 2, 40% every decade. Adjust the rate of decay to find it annually. So it starts out for 40% every decade. So put a 1/10 and a 10. A 1/10 and a 10. Add that, and you can convert that. And there are 2 problems there as well. Grows 55% a week. Convert it to daily. So add a 1/7 and a 7 in your equations here. All right, let's look at the assignment that goes with this one. Which log function is represented in the table? You got to figure out, is this log x of 5? Is this 6 log x? Is this the log of 6 to the x power? Or is this log base 6 of x? Log x equals 4. What's the answer? What is x? What is x? What's the base? There's no base. That means it's automatically base 10, right? 10 to the 4th power. Evaluate the natural log of 5. That's a calculator problem. Oh, I told you about the calculator in here. Like on this one, if I want to do the log of 100, this one you hit the log button first. It's right here, log, and see it shows the parentheses. What is the log of 100? It's 2, because 10 squared is 100. So on this one, you can hit the button first. If I want to know the natural log of 5, it's 1.609. Hey, look at there. I got one answer done. All right, solve 3x plus 1 equals 15. Use the change of base formula. Rewrite this as a logarithm, then use the change of base formula and see which answer you get. And here is one of those problems like we solved, that long problem. You $5,000 in the savings account. You want to have $6,000 for a new car. You get 7% per year, and it's compounded every month. So how long is it going to take you to get $6,000? So basically, $1,000 in interest takes how long? Is it 300 years? Is it 31 years? Is it 26 years? Or well, 2.5 years? Get it? So solve that one. And there's it. 5 problems. 5 problems. Yes, I know I haven't finished. All right, let's look at the mid-module check, basically a little quiz. This just says make sure to do this quiz right here. See how many questions it is. 5 questions, just 5 questions on the mid-module check. Solve this. This is the exponential equation. This was from the first lesson. This was from last week's lesson. This is also from last week's lesson. This is where you plug the numbers in and see how much money you'll earn in 12 years. And it tells you to use the A equals PERT. So this one uses E in your calculator. For this calculator, where's the E? It's right here in the corner. E equals 2.718281828. So there's the E button. Okay, this is from the second lesson. Solve this log of x equals 2. Solve this. 4x minus 5 equals 6. Just use the change of base formula. And here's the one you have to show your work. Okay, that's a different one than this, but it's very similar. Explain how to solve this using the change of base formula and include the solution. So basically, you don't have to use words. If you just show all the steps, that explains it. It says round your answer to the nearest thousandth. That's 3 decimals. So start out with this, but that is your first thing. And here's where it gets important, guys. If you haven't figured this out yet, there's a button right over here that says insert equation. If I click this, I can put 4 raised to the power of x plus 3 equals 7. That's what I type, and look what it looks like. Or it looks just like this using the insert equation. And then I would rewrite that as a log, insert equation. Log of, let's see. Insert symbol down here. It'll show somewhere. Where's the log? Oh, it's one of these. X to the Z. Okay. So log underscore 4 of 7 equals x plus 3. So I can rewrite it as a log base 4. When you look at the insert equation, it shows you that if you type log and then hit this button, it'll do that underscore. If I type log and then I said, I want a little subscript number. So say whatever number I type after that little underscore, it makes it a base, log base 6. But there, rewrite it and then continue with the steps. And it says use the change of base formula. So the next thing I would need to do was show the change of base formula. All right, and if you struggle with that, use parentheses. Like if I was doing x plus 1 divided by x minus 2, and like, see, that doesn't even look right. But if I put parentheses around everything I want to be in the numerator and put parentheses around everything I want to be in the denominator, now it looks right. So you got to use parentheses if you're dividing and trying to put complicated expression on top or bottom. If it's just one thing, it's x divided by x plus 2. I don't need the parentheses. I can just say x divided. But when I put something with the x, I need to use parentheses to keep it together so it knows all of it is in the numerator. So, all right. Just showing you that insert equation button is especially important when we're doing all this log work and change of base and exponents and all this, or your work is going to get so confusing you're going to get lost in it. And it probably helps to do it on paper first and then try to convert it to something here. But this is the quiz that goes with that. So you've got about 15 minutes left of class. You can get started on this before your next class if you like. I'll give you that time to yourself. I'm through. So I will let you guys go and you can get started on this. You may be able to finish it. 2 5-question assignments. Maybe not. Get your pencil paper out, get some work. Make sure you understand. We'll catch you guys next time. Have a great week.